Greetings, good morning or good afternoon, depending on where you are. My name is Professor Duke Orata. We are continuing with our lecture series in thermodynamics, and today we want to look at shear stress in fluid flow. Now, we have talked of fluid flow, and we have said that there are two types precisely of fluid flow. We normally have the laminar or the streamlined fluid flow, where the flowing fluid does not interfere with the adjacent elements in its path. And also we have talked about turbulent flow, and we said that turbulent flow are actually caused by velocity gradients within the fluid, and so there's generation of eddy currents within that particular system. And we have looked and seen at the boundary layer patterns or profiles for these particular systems. And when we talked about the turbulent system, remember we talked about the Reynolds model, decomposition model, where we had the expected value and the varying velocities, because in a turbulent environment, the fluid dynamics are not linear. They are non-linear, and so there is a lot of variation, change in velocity with time, and we say that the varying ones, the mean is actually zero. So let us narrow down to shear stress analysis in this flow system. Now, always remember, anytime you're talking about when you're talking about shear stress, always remember that equation which we derived first time. Don't forget tau. And we said that tau was mu u dy, or you can also say tau is rho v the mu dy. And we had said that this mu here, that is the dynamic viscosity. Dynamic viscosity. Don't forget. And you also say that V here is the kinematic viscosity. And that, of course, is the density. Now, even as we are going to look at the eddies, which are basically related to the shear stress in the fluid flow, always remember that even in the turbulent region, there is a sublayer next to the wall which is experiencing laminar flow. Always remember, even in the turbulent region, next to the wall is a sublayer of laminar flow. So let's just have a profile which can illustrate that. So we resolve our velocity into two components. So we have let's say that in this region, let us say that's the x-axis, that's the y-axis, and this y-axis we are associating with the velocity v, and the x-axis we are associating with the velocity u. Note again, u and v. U is velocity along x-axis, and v is velocity along y-axis. And so, this is the turbulent layer region. turbulence here. We have kind of laminar flow. And let's say here there's a boundary. There's a transition between laminar and turbulent flow. And so let us focus in some region here. Let us call it between x1 to x1 prime. And let's say that there is shear stress. That particular region. Now, how do you go about developing these expressions? Now, one, in the turbulent region, we have said that the velocity varies. And so, because of those perturbations resulting from the eddy currents within that particular system, we will have the variational component of the velocity which is resulting from that perturbation of the fluid flow system in that turbulent region. And so if we resolve our velocities along the x and y direction, and also remember, we have said this is the turbulence region, the turbulence region. Let us say that it is some distance y1 from the wall, turbulent distance y1 from the wall, turbulent region, some distance from the wall. And you have said that x1 to x prime is the region eddy currents which are responsible for the turbulence because of those velocity gradients. Now, if we resolve this, the velocity, we have the y direction where the velocity is v, and u direction where the velocity is u. So we have resolved the velocity into two components. U and V. Now, in the turbulent region, there are two things which happen. There is mass transfer, which results, and there could be transfer of momentum, which could be affected by molecular carriers or macroscopic elements. So in the turbulent region, there is mass transfer, mass exchange, and transfer of momentum. By, we have said, macroscopic or molecular carriers. And so that means that using the equation which we are used to for shear stress, we must modify it to factor in some of this particular element. I repeat, there's mass transfer and there's also transfer momentum by those carriers there. And so let us now narrow down to factor these quantities and see what kind of expression can account for the reality on the ground in the turbulent layer. Now, we need the side of the board. Remember from continuity equation, we say that the mass flow rate, because we are talking of mass transfer, therefore the mass flow rate that is mass per unit time. is gotten from the product density times area times velocity, where rho is density, we are already familiar with that, A is area, and V is velocity. And I keep encouraging you, please kindly go through those other lectures so that we have built up these concepts. We build them systematically. So if you follow them systematically, then they become very simple. Now, this is mass flow rate. If you do dimension analysis, just to convince yourself that this is mass flow rate, density is mass over volume, area is length squared, velocity is length over time. So length cubed cancels velocity. So we have mass over time. And that is flow rate. And so we are saying that when there is this upwelling as a result of the eddy currents, which we have said is the result of velocity gradients in the fluid flow system, then the mass which is transferred we can get that simply by multiplying that by the time interval. Therefore, the mass transferred we just get it by multiplying by the time interval for the unit volume, the T. We are assuming we are dealing with unit area to make our calculations easy. So that's the mass transferred. But we know, we have talked of transfer of momentum. We know what momentum is. Momentum is the product of mass and the velocity. And now we have the mass here. This is the mass. So if we multiply that, just have this diagram in your mind. Always have that diagram in your mind so that when you cross-reference it, you remember. So, in terms of momentum, transferred, we have mass times velocity. Momentum, remember, mass times velocity. And what is our mass here? Is v dt times velocity. So we have our two velocities there. But if you look, think about it, the shear stress in the eddy region is basically the rate of momentum, or the momentum rate. So you remember we have that, our diagram schematic. It's not the best, but we said the shear force is there. And we are saying that the shear force is there. Shear stress is basically the rate of momentum, or momentum rate. And so that is how momentum varies with time. Let us look at that. Momentum, we just said that. So the tau, we are saying, is related to the rate of momentum, which will be mv over time. And so what is that? That is mass times velocity, you know, is length, distance, and now will be time squared. So if you look at this, for example, in actual units so that you grasp what you're talking about, it will be kilograms, length is in meters per second squared. And what is that? mass, that's acceleration. That is mass. And what is that? Newton second. Phi F is equals to ma. So that's shear stress. The system is like the rate of momentum or the momentum rate. Now, when we factor all these quantities, so we are saying that tau, therefore, the shear stress, tau, the shear stress, we have said is the rate of momentum. And what was momentum? We have said this, remember, was mass, times velocity, that's momentum. So it's rho t, velocity, over time. So if we rearrange this quantity so that we get main values, remember, now we define u. That's the instantaneous velocity, is the main velocity plus the velocity component resulting from perturbation of the fluid flow as a result of those eddy currents. This is the instantaneous velocity. This is the main velocity, and that is the perturbed velocity or the variation, velocity as a result of the eddy currents. Similarly, in the v-axis, in the y-axis, we have the same, with the same meaning. That's the instantaneous velocity, the mean velocity, and the velocity varying as a result of those perturbations. Now, if we integrate the quantity here, get these main values, then what are we going to have? We're going to have that tau is equals to rho v over t integral from some time limit, and you know what u is, 1 plus prime into v bar 1 plus prime dt. That is u. So if you open up this bracket there, if you open up that bracket there, our life becomes very simple. If you open up those brackets there, and have this quantity here, that is the main velocity on y, the main velocity u, and that of v1. So we'll have tau is equals to v over t, then we have u bar 1, so we multiply that with that, of course, and then multiply that, the second one, so u bar 1 times prime plus u1 prime 1 plus, that is that, plus v bar 1, and then prime t. So, one of the first things which you take note of is that these two quantities, like you have said, will vanish. Those perturbed velocities, we had said the main, based on the Reynolds decomposition, will be 0. Therefore, what we are saying is t of 1, same as A V of t 0 t prime 1 v bar 1. This will be 0. That will be 0. Remember, we talked of the expected value is the mean value, and we're talking of the variations as a result of the velocity gradients, which are the eddies in the system, and those are 0. So we are left with tau will be a v t, the integrals to t of bar 1 plus 1 prime v1 prime dt. So if you solve that, very, very simple. That's a very simple solution. Very, very simple solution. Now the solution tau, therefore, tau, if you look at this, take the integral of that, t will have rho v over t into u1 v bar 1 plus u1 prime v bar 1 prime t. The t's will cancel out, so we have rho av into bar 1 v bar 1 plus u prime v bar 1 for tau. Remember, we talked of unit areas and so forth, but you don't want to remove them so that you're able, in terms of dimension analysis, for you to always remember what we are talking about. For you to remember what we are talking about. Now, if, for example, the mass transfer, remember, let's have some coordinates. So we are saying that if we have our coordinate y and x-axis, these are of course u, that is v, and that's of course u. So we are saying if this transfer from the wall upwards, mass transfer, that will be positive. If it is downwards, that will be negative. Very important for us to have that configuration in our mind. So what are we saying? We are saying that if, for example, the transfer is simply predominantly along the v-axis, is the y-axis as opposed to the x-axis, then there will be, in terms of mean velocities, there will be, this quantity will vanish. If most of the transfer along that is along y-axis, transfer along y-axis, then v dominates. And u is 0. And so we will have tau as rho a v into u prime v prime v1 prime prime. And therefore, this we can equate to the as our AD, shear transformation, the eddy transformation. In this particular case, we are saying that we have rho over v, u prime, v prime, and that. And remember, these quantities, they don't necessarily have to cancel out. Remember, this is in the u direction, this is in the v direction, so they don't have to cancel out. But we say that if the transfer is predominantly along the y-axis, then that v will dominate, and this mu bar will be 0, so we can treat that quantity there as 0. So, this our expression here is now the shear stress associated with this eddy currents. Eddy currents. So we can say that is rho AV into U1 prime, V1 prime. And that is equal to rho. Let's have eddy current, du dy, where we can now call this eddy diffusivity. We have seen several of this. If you kindly refer to our lectures, we have seen several of this. We have talked about momentum diffusivity. We have talked about thermal diffusivity. We have talked about mass diffusivity. So we can equate this and say this is the same as eddy diffusivity. Now, so what does that do to us? So we are saying this is the eddy shear stress. Eddy shear stress. Let's just call it eddy shear stress. So that what are we saying? We are saying that in a nutshell that the total shear stress in that system can now be thought of as being two-faced. We have the viscous component and we have the shear stress component. So that the total shear stress the shear, we have the eddy component plus the viscous component. So that what we now have is that for that total shear stress total is E plus what we know, not forgetting that that is dynamic viscosity. It's dynamic viscosity. So, in a nutshell, what we are saying is very simple. We have seen that, as we have said, in fact, we say that turbulence normally starts at Reynolds numbers. Turbulence, just for your note, remember, please go through our earlier lectures kindly. Turbulence starts at about Reynolds number of greater than 2300. And what was Reynolds number? What was Reynolds number? We say that was rho AV over mu. Over mu. That was Reynolds number. And so we say that turbulence commences at about Reynolds number greater than 2300. Greater than 2300. So when you're having fluid flow, like we had said, in pipes, you want to operate at below 2300. And what's the original turbulence? We have spoken about that, the eddy currents. Now we have looked at the shear stress in the eddy region, where we have those mass transfers, which basically the shear stress is the rate of momentum in transfer. And we have come up and we have seen that we now have the total expression for the shear stress. We will pick up with other lectures as we continue. So let's stop at that point.